One of the benefits of an application problem is it's often visual. It's often something that we can picture and thus draw a picture of. We can look at the parts of the graph. So what I'm going to do is try and draw a picture of what's being represented here, and then maybe label some parts. So it says the light of a lampshade casts a hyperbolic pattern on a wall due to its lampshade. So that gives us a good amount. Right away we have this lamp, and I'm not going to pretend to be able to draw a lamp, so I'm going to draw something like that. The lampshade causes this hyperbolic pattern on a wall. Something like that. Determine the equation of the hyperbola if the distance between the vertices, so vertices being here and here, is 3 feet, and the foci are half a foot from the vertices. So there's a distance of 3 feet. So let's redraw that. Distance of 3 feet here, and there's 1/2 foot from here and in the other direction. In order to form the equation, we might want to know the general equation of a hyperbola. So it looks something like x minus h squared over a squared plus y minus k squared, or excuse me, plus is for an ellipse, minus is for hyperbola, over b squared. Additionally, we also want to make one little more change to this, which is this is for the horizontal version of the hyperbola. This one, as you can see, goes up and down, so it's the vertical version. So what I'm going to do is switch around my x and my y here. This should be y minus k squared and x minus h squared. All right. Now, h and k are the x and y values of the center. Now the center can be placed wherever we want, so I'm just going to place it right at the center, right at the origin, excuse me, and that is, it's going to be placed at 0, 0. That means our new equation is y squared, y minus 0, right, squared, y squared over a squared minus x squared over b squared. Now I want to find my a and my b before I finish filling out this formula here, this equation. And we know some properties. We know that this measurement right here is a, which as you can see is just half of 3, so it's 1.5. So this is 1.5 squared right here. Now b is a little more complex. We actually know one extra value on top of a, b, h, and k. We also know c. We can figure out c from this image. Notice that, or recall that rather, that c is the distance from the center to a focus. That's c right there. And since this is 1.5 from here to here, and this is 0.5 from here to here, then you add those together and that's c. So c then is equal to 2. We can then create the equation, as with any hyperbola, that c squared is equal to a squared plus b squared. And since we know a and we know c, we can find b just by solving the equation. Recall that a, b, and c are always positive, so we don't need to worry about the negative version from the square root. C squared, since c is 2, we have 2 squared equals 1.5 squared plus b squared. And we can do some simplification here. I'm going to treat 1.5 as a fraction, so I'm going to treat it as 3 halves. 2 squared is 4. 1.5 squared would be 9/4. And then I'm going to subtract the 9/4 from both sides. 4 minus 9/4 is the same thing as 16 minus 9/4, which is 5/9, and your calculator will tell you the same thing. Then we take the square root of both sides, and we get b squared is equal to that plus or minus square root of 5/4. Or excuse me, this should be 16 minus 9. Maybe it won't tell you the same thing. It'll probably tell you 7. A little bit of a computational error, but an easy fix nonetheless. All right, knowing this, we don't actually have that square root there, or the square here anymore. We know b is equal to plus or minus the square root of 7/4. Now, we only care about the positive version, but even more than that, we actually don't even care about what b is. What we care about is b squared. Notice that this formula only uses b squared. If b squared is equal to 7/4, then I can put 7/4 down here. And this is our equation then.